This video is a walkthrough of the complete process of designing and simulating a complete SoC using the Vivado design environment. As such, it is absolutely essential that you follow along with the video and also complete the steps on your own. In fact, I would strongly recommend that even those who are otherwise familiar with the Vivado tools should perform this exercise, or at least make sure that they go through the video and are familiar with all the tools required, especially the design environment, which is not a standard setup and will be used for all the experiments and exercises that follow. Keep in mind that the Vivado design tools are an industrial strength suite of tools. Unfortunately, this means they are fairly slow and not really geared towards quick and dirty experiments such as this exercise. You will most likely require upwards of 1 hour to complete this exercise. I have extensively edited the video to trim over all the portions where the tools take a long time to respond. You should be able to identify those spots in the video and pause them and allow yourself time to catch up. The objective of this exercise is to simulate a complete, although very basic, system on chip. What we will do is build a basic SoC using the Vivado design environment. The SoC will consist of a CPU to execute a program, memory where the program will be stored, and one peripheral which is a general purpose input-output pin. In this case, just used as one output. We will write a program using the Vivado software development kit. The program will essentially cause the GPIO output to toggle. And this entire system will be simulated using the Vivado simulator. In this exercise, the only custom Verilog that we need to write is for the test bench. The rest of the design is automatically generated by the tools. However, it is strongly recommended that you familiarize yourself with the basics of Verilog, in particular with how to write and read test benches and how to interpret simulation waveforms. We are going to create a project in the Vivado Design Suite software to create a basic microcontroller plus one simple peripheral, write a simple program for it, and run it in simulation. So for that, start by invoking the Vivado software. So once it has come up, you can use the quick start menu, click on create project to start a new project. Click on next. You can use the project name as project 1 or anything else that you like. Project location, once again, choose something that you would remember and is suitable for you. Make sure that RTL project is selected, that is the default. We will leave all of the most of the remaining entries at their default values, so we will not be specifying any sources. Click on next. No constraints. The part number that we are going to choose is one that is used in the Basis 3 board that is available in our lab at IIT Madras. It uses an RTX 7 FPGA. However, since we are only doing simulation, it doesn't really matter what part you choose. You are free to choose some other part. Keep in mind that in the Webpack edition, you have fairly stringent limitations on the parts that are permitted to be synthesized and simulated. So if you choose a large FPGA part, you might find suddenly later on down the line that it does not either generate a bit stream or does not even simulate. The RTX part that we choose over here is probably a safe bet anyway. The part number is XC7A35D CPG 236 and -1. All right, finish. So you can see that it brings up a window that has a project summary and a few other sections over there, including a summary of the design runs, some properties, sources, and so on. Since we have not yet created anything in the project, most of it is blank. On the left-hand side, under the IP Integrator tab, you can see that there is an option to create a block design. That's what we are going to do. You can give the design any name that you want. In general, both for files, projects, anything that you are creating, avoid using spaces in the names, but apart from that, you are free to name it anything that you like. All right, so it brings up a section called the diagram where it says this design is empty. Press the plus button to add IP. So we'll go ahead and press that. Type in the first few letters of Microblaze and it should filter down to that. So you can select Microblaze, double click on it. It will add a basic Microblaze processor to your design. You'll notice that there is an option there to run block automation. Go ahead and click on that. The options that it gives you, basically, we don't want to choose any of the preset options. We are creating a custom design over here. What we do want to do is to change the amount of local memory from 8 KB to 128 KB. This is probably not very important in our initial designs, but might matter later. Leave the other things alone. For the clock connection alone, rather than new clocking wizard, just change it to new external port. Click on OK. Now we can go in there and click on the plus button one more time, add IP, and select the option GPIO. It brings up AXI GPIO. Press enter or double click and that should instantiate the module. Now, before going through the connection automation, which will basically set up our ports properly for us, let us configure the GPIO properly. Double click on it. And over here, we are going to set it to all outputs and change the width to 1. You might notice that some of the windows in the Xilinx software tend to be really large and spill out of your screen. Unfortunately, that's just an aspect of how the software is. There's not really much we can do about it. Now you can click on Run Connection Automation and click on the topmost checkbox, which will basically select everything else. It will activate the GPIO, the S_AXI, and the external reset in. All of these will just get connected automatically once we click on the OK button, which basically means that the GPIO device, which is an AXI peripheral as far as the Microblaze processor is concerned, will be connected to the processor, and the reset button will be made an external port. Okay. You can click on this button on the top over here that says Regenerate Layout. It will just clean up the diagram a little bit. I'm just going to zoom this picture in a little bit so that you can see it a bit more clearly. What you can see is that on essentially what we have now is there is a central microprocessor. There is a debug module that you can ignore for now. There is also a reset and clocking module whose purpose is basically to make sure that the reset and clock signal get distributed properly to all the peripherals as well as the Microblaze. There is a Microblaze local memory module that is basically the 128 kilobytes of memory that we had instantiated. There is an AXI peripheral, the interconnect or arbiter, which takes care of connecting the single peripheral in this case, which is a GPIO peripheral, a general purpose IO peripheral, to the Microblaze. Once again, one thing we can do is go look at the address editor. And if we open the Microblaze tab, you'll find that under data, there is the local memory, which is on the slave local memory bus, 128K locations. And there is the GPIO, which has been assigned 64K locations automatically. Now, if you think about it, the GPIO is just a single bit. That's all that we are going to be writing over here. It's not even a readable port. So it's a complete waste of space to allocate 64K locations to it, but we don't really care because those memory locations are not being used for anything else. The instruction memory, as you can see before, overlaps completely with the data memory, so they're basically the same. Going back to the diagram out here. The next step after this is that we need to create an HDL wrapper, a Verilog wrapper for this module. So if you click on the sources tab in the middle section, you'll find that under design sources, there is something that says design 1 .bd. Right click on this and select Create HDL Wrapper. Leave it at the default. Let Vivado manage wrapper and auto update. Okay. So what this does is that it creates a .v file, design1 underscore wrapper.v. And if you open it, you will find that it doesn't really have any content. It just basically has a total overall wrapper, which basically gives the signals. There's a clock, a GPIO RTL, and a reset underscore RTL. And it has an instantiation of the design underscore one module. Now, as far as we are concerned, the only reason why this is relevant is that we will be using it later and instantiating it in our test bench. And also when we finally create an actual system to run on the board, we will need to use these signal names in order to map them to the different ports of the system. Okay, so now everything is done. What we need to do is basically go here and click on this button, Generate Block Design. What will happen as a result of this is that you will get this option over here saying Generate Output Products, and it will bring up the option to basically generate all the output products corresponding to the design that you have created. The synthesis options, it says, is out of context per IP. Leave that as it is. The run settings on the local host, number of jobs, you can either leave it at the default. It will pick some sensible default based on the number of processors that you have on your system, or you can max it out, set it to the maximum number 4. In my case, since this is the machine has 4 virtual cores, it has a maximum option of 4, but the default it chooses is 2. Click on Generate. This will basically start to generate the output products. I'm going to skip ahead at this point because this takes quite a lot of time on my machine and I have already generated the products separately. We will just skip over to that. So this is what the design looks like once the synthesis has been completed. One thing you might note is that some of the names of the signals might be a little different in this project than what I had originally shown in the earlier part of the video. Just ignore that. You can basically rename the signals to anything you want in the block design, and the same things will get reflected in the design wrapper as well. If you click on the Design Runs tab at the bottom, you can see that there is some information about how many lookup tables and flip-flops and so on are actually used for the different parts of the design. This is not really important at the moment, but it's good to know because later on when you actually start your own hardware designs, you will be constrained by the amount of hardware that's available to you. And it's good to sort of have an idea of how much space on the FPGA is occupied by different types of modules. Once you are satisfied that the generation of products has completed successfully, normally the next step that we would be doing would be to go through the generation of the bit stream and generating final output products. That's only if you're going to run it on an FPGA. In our case, we are going to stick to simulation, so we don't really need to do that, and we are going to skip that part at the moment. What you need to do is select File, Export, and click on Export Hardware. Do not select the include bitstream option, just leave it unchecked as it is. Export to local project, leave that at the default and click OK. After that, we can go to File and launch SDK. The reason for this is that we need to create the executable program that is going to run on our processor. And the SDK or the software development kit is where that gets done. When the SDK window comes up, you should see that it has imported the hardware specification and it should give you some details about your hardware platform. At the top, you have the target FPGA device, which is the 7A35D, the Arctic 7 from Xilinx. And most importantly, you should find that the address map corresponds to the entries that you had put in while designing the system to start with. In our case, we have an AXI GPIO. The base address is 400, etc. And the high address is 4000FFFF, which is basically the 64K address space allocated for the GPIO. And you have the microblaze local memory, which occupies 128 kilobytes of memory. This is just the memory map of the processor, which of course should correspond to what you had designed to start with. What we need to do now is to generate the executable file. For that, we are going to start with File, New, Application Project. Give it any name that you like. In our case, I'm going to give it the name GPIO test. Use default location. OS platform remains at standalone. The hardware platform is Design 1 Wrapper HW Platform 0. You should see just that along with a few other options which are predefined. Do not choose the predefined options. Choose the one that you have generated for yourself. The processor, in this case, you should only see a Microblaze 0 because there's only a single processor there. Language C or C++, you have two options over there. The compiler, hypervisor, etc. You don't really have any options. Board support package, click on create new. We do not have any other board support packages, so we'll just leave it as it is. Now the board support package essentially is a set of library functions that allow you to access the various devices and peripherals that you have got on your board. In our case, it's only a simulation based setup, but still it's useful to have a board support. It's necessary to have a board support package. Click on next. Normally, we would probably choose something like the Hello World application as the first one that we want, but in our case, we don't really have a serial port to print on. So I'm just going to start with an empty application. You can just select empty application and click on finish. So you see that there is a system.mss tab that is generated. This is basically a description of the board support package. It gives you some more information about the target. The operating system in this case is standalone. And the drivers that are present, the main thing that you need to see is there is a driver corresponding to the AXI GPIO 0. There is also something for the data and instruction memory controllers, but those are not things that we will be touching at all. On the left hand side, you will notice that two new tabs have opened up, GPIO test and GPIO test BSP. Opening the GPIO test underscore BSP tab is informative. You can see that there is a Microblaze under it. And in particular, if you open the lib src tab, you will find that over there, there is one section that talks about the GPIO. And when you open src, you will find all the files corresponding to the GPIO module that has been included. In our case, the GPIO is an existing module already designed by Xilinx. But if you create your own modules using Vivado HLS, you will find that they will also get entries over here, and they will also come along with a set of C and .h files that will help you to write programs for to control that module. We can open the xgpio.h file. That basically gives us a lot more information. You can read through this at your leisure. The important thing that we need to keep in mind are a couple of things. Going down here, you will notice that there is something called a typedef struct GPIO. This is the basic structure in C that we will be using in order to communicate with our GPIO device. We will need to use the GPIO initialize function in order to actually set it up and set up all the memory interfaces and addresses corresponding to that inside the processor. And finally, we will be using this command GPIO underscore discrete write in order to actually change the values on the GPIO. So let's go ahead and create a program that does this. I'm just going to write the fresh program from scratch. You can go to File, New, Source File. For source folder, browse to GPIO test and SRC. Do not put it under other folders such as the BSP and so on. That will totally clutter up your workspace and make it difficult for you to keep track of what's happening later. Put it under SRC and OK. You can call the file anything you want. GPIO test.c is probably a good name. And that basically opens up editor. Now, how do we actually write the code in order to access our GPIO module? First things first, we need to include that header file that I just showed you earlier. Hash include x, oops, there's a typo there. That should be x gpio.h. And we can now declare the main function. Remember that main needs to return a value, otherwise it will complain about that. So I'm just going to put that in there, but make sure that's only the last line in the program. All right, so now how do we actually communicate with the GPIO device? We need to instantiate it. I'm going to call it XG. So this has basically created the structure to communicate with the GPIO device. Call the GPIO initialize function. This takes the address of the structure that you just created and something called the device ID, which unless you have multiple instances of a particular type of module will be 0. The first instance of any device type will be 0. Other instances will have different numbers over there. So we have initialized the device. Now what I'm going to do is just create a while loop, while 1, so it will never terminate. And what this is going to do is to do X GPIO discrete write to the structure that we had earlier, channel number 1, and the data I'm going to write is 1. If we go back to the xgpio.h, you will notice that the information it requires is, first of all, the pointer to the structure. The second argument is something called the channel number, which in our case is 1. The default channel is 1. And an unsigned 32-bit value, which is the mask. Again, this is actually the set of 1s and 0 bits that are to be set out to the GPIO. In our case, we have only 1 bit. So I'm just going to write the value 1 directly. And then what I'm going to do is just take this entire thing and repeat it over here, except that the second time around, I will write 0. So what should this program do? It should go into an endless loop, which basically just writes 1 followed by 0 to the GPIO pin. Save the file, and you should notice as soon as you save that down at the bottom, if you click on the console, you should see a bunch of messages which finally end with something saying that the file gpio-test.elf was generated, and of course some output information corresponding to that. If you see any problems, there are errors. Warnings are maybe okay to ignore. In this case, it's basically complaining about the way that I've written the code, but it does not really matter too much. You can ignore it for the most part. Well, actually, no, these warnings are nothing to do with the code that I've written. It's more to do with something else in the board support package, so you can safely ignore it. As long as there are no errors over there, you should be fine. It would have created a file called gpio-test.elf. Right, now we can switch back to Vivado. And what we need to do over here is the next part, which is basically we are going to create a simulation test bench. For that, we will go to the project manager, click on add sources, add or create simulation sources, not design sources, and click on create a file. Give it any name you want. I'm going to call it system_tb, file location local to project. Okay, and click on finish. It brings up some information which allows you to add module input output definitions. A test bench usually does not have inputs or outputs, so we'll just skip that and click on OK. Are you sure? Yes. Now this should basically create a test bench module. Takes a little while to update, but once it has done that, we should be able to go to the simulation sources, sim_1, and if you double click on system_tb, it should open up and show you that this is basically an empty module. So now what we are going to do is to instantiate our design wrapper. Right? If we open the design wrapper, we will see that it basically has 2 inputs, clock and reset, and 1 output, which is the GPIO try_0 signal. I'm just going to start by copying this module definition over into system_tb. Paste it over there. Just delete the word module. And instead, at the end of the line, put in DUT. DUT is a standard abbreviation that stands for design under test. What I'm going to do now is use the instantiation of the Verilog signals. Internally, I'm going to use the signal CLK with a small letter C in order to indicate the clock. It doesn't really matter whether you use small letter or capital letter, but it is case sensitive. So if you use small, then use small everywhere. .gpio try underscore 0, I will map that to a signal called GPIO. And .reset, I will map that to another signal called reset. Now, what I need to do is I have declared the connections of the design under test. What I need to do is declare the signals themselves. So I need to create a register for the clock, another register for the reset signal, and a wire for the GPIO. Why are these required? Because basically the way that we are going to be doing it is that the clock and the reset will be assigned signals from the test bench. They will go as inputs to the device under test. And the GPIO will be a wire that basically picks up the signal that's coming out from the design under test. DUT is either device or design under test. All right, so how do we actually go about creating a clock signal? The first thing is we have to set up some initial values. I'm going to set the initial value of the clock equal to 1, and it'll then toggle after that. Set the initial value of the reset to 0. The reason for this is that this is an active low reset that the system uses. So what I can then do is hash 100, which is basically after 100 nanoseconds. I'll make reset equal to 1. And that's it. I'm not going to provide any other values for the signals. Now I need to make sure that the clock toggles. The way that I'm going to do that is to use this always block. Always after 5 nanoseconds, clock is equal to tilde clock. What this does is basically create a toggling signal which has a time period of 10 nanoseconds or 100 megahertz, and will apply that as an input to the test bench. That's pretty much all that we need as far as the test bench is concerned. I'll just save this file, and once I save it, you will notice in the middle pane that this updating icon shows up, and after that you should find that the design wrapper has gone under the system underscore TB in terms of the hierarchy. The system underscore TB has become the top level module, and as far as simulation is concerned, that is now the one that is ready to be simulated. One more step is needed before we actually run the simulation. The ELF file that was generated using the SDK, we need to associate it with the software that we have, or with the system that we have over here. Go to the simulation sources, right click on design underscore 1 underscore I, the triangle, the orange shaped symbols that we have over here, orange colored symbols that we have over here. Right click on it, and you should see an option that says associate ELF files. I'm going to change it only for the simulation sources. What needs to be done is you click on add files, go to project2.sdk. You should see the directory GPIO test. Go to the debug directory there, and here you should see the GPIO test.elf that you had created using the SDK earlier. Click on OK, and you should see that it basically comes up under ELF files. In my case, I had already added it, so it was already there in the list. In your case, you would probably only see the mb underscore bootloop underscore le, which is the default. You'll need to add the ELF file using the add files option. Make sure that that's the one that's selected and click on OK. Now you should see that GPIO test.elf is the one that's going to run for simulation sources. All right, click OK. We are all set. Now we need to run the simulation. Make sure that you have clicked on system underscore TB before you click on run simulation, because if not, then it will pick whatever you have clicked on and try to simulate that. So select system underscore TB and then click on run simulation, run behavioral simulation. This should do some compilation steps and then bring up the simulator. All right, once the simulator has come up, you should see a few different window panes over here. You can resize them, move them around so that it becomes a bit more visible. As you can see, pretty much only 3 signals are showing up right now: the clock, the reset, and the GPIO. Those are the top level test bench signals. Those are the only ones that really show up. This signal over here and this button over here that says zoom fit, when you click on it, you will find that it basically zooms and brings the entire uh, simulation time period into the window. That's probably a good idea to do at regular intervals, because otherwise you sometimes click on the run button and think that nothing has happened. In this case, what has actually happened is the simulation started and already ran for a period of 1 microsecond, that is 1000 nanoseconds, and this is the result that it's showing. What you can see is that the clock has essentially gone through 100 cycles during that time. The reset signal was low for the first 100 nanoseconds and then became high at the time 100 nanoseconds. And the GPIO signal is showing no signs of activity so far. So let's run this a bit further. If you go click over here, you have an option of run for 10 microseconds. You can also change that to any other number that you want. 10 microseconds is probably a good option. So we click on 10 microseconds and it should run pretty soon. Once again, you need to click on zoom fit. And now suddenly you should notice that things have changed over here. The GPIO signal that we had that was initially low has suddenly started toggling. Now, what happened over there? What you can see is that the first signs of activity on the GPIO signal are only at 3.7 microseconds, right? The reason for this is that it took that long for the system to actually initialize, load up the ELF file, and get to the point where it actually started running the while loop, right? So the GPIO initialization and all those other things were happening before that. At 3.7 microseconds, the first instruction in the while loop, which basically said write 1 to the GPIO output, was encountered, and that GPIO signal got updated, or rather that instruction was encountered a little bit before 3.7 microseconds, but by the time it had an effect at the output, it was 3.7 microseconds. Now, the interesting thing you would notice is normally you would expect that in the very next clock cycle, the very next instruction should have taken the GPIO signal low again, because after all, that's what our code looks like over here, right? We are just toggling between 1 and 0. But what you can see in practice is that if you click on the point where it went low, that happens at 4.11 microseconds. In other words, we have time from 3,700 nanoseconds up to 4,110 nanoseconds. That is 410 nanoseconds or 41 clock cycles passed, during which time the GPIO signal was high. Okay, so in other words, to go from one instruction of XGPIO discrete write to the next one basically took 41 clock cycles for the microblaze processor. Is that slow? Probably yes. This processor is not really designed for speed. Why should it take 41 clock cycles to just toggle a port? Well, if you want it faster, then that's where you write custom hardware. And of course, what you can also see is after a certain amount of time, that is 4.55. So in this case, 44, I think 4.55 minus 4.11, yeah, 44 clock cycles, you have the signal going back up again. So that includes the 41 clock cycles for the XGPIO and 3 clock cycles overhead for the while loop. And from there onwards, you should find that it's basically pretty much a repetitive pattern that you see from there, right? And if you continue simulating, you will find that this goes on endlessly. There are a couple of interesting things that you can do. If you go to the scope window, you can actually open down into the design and go all the way down into the microblaze processor itself. You can actually go look at the microblaze processor and in this case bring out the instruction address and in fact the exact instruction itself that is being executed, right? So you'll see that there's a 32-bit instruction address that's being sent out by the microblaze processor and a 32-bit instruction. The values don't show up on the waveform because they were not recorded for the simulation. You can either relaunch or just continue to run a little bit longer. And you will find that when you zoom in over there, you can actually see the instruction addresses changing. And if you look at the addresses carefully, you will notice that on every clock cycle, they basically change by 4, which is 32 bits or 4 bytes. And on every clock cycle, in other words, a new instruction is being read in. The actual instructions are there below. You probably can't really interpret them unless you know the machine language of the microblaze, but the information is available to you if you want it. So this was essentially a demonstration of how you can write a simple program, compile it, and run it on the design that you have generated in the microblaze. In future exercises, we'll be going through actual accelerators where we try and identify portions of a program that are slow and see what we can do to make them run faster.